Welcome to Lecture 2 of the final week of the class Neuronal Dynamics. I finished the previous lecture with the statement that things are missing in the nonlinear integrated fire model, that it cannot account for adaptation, that it cannot account for different firing patterns. Now let's address these issues now. What is adaptation? Well, an experimentalist injects routinely a step current into neurons, and he observes behavior. And typically, what you find quite often is a behavior like this. There are first a sequence of spikes with very short interspike intervals, and as we wait, the interspike intervals get longer and longer. This is called adaptation. For small input, the effect is sometimes very big. The final interspike interval is much longer than the first one. If you increase the input current, the neuron is still adapting. Overall, the interspike intervals are shorter compared to the low input case, but still it's true that the final interspike interval is longer than the first one. That's adaptation. Now, some neurons show sort of an extreme form of adaptation. In fact, it's not just adaptation. There's a burst at the beginning, at the transient, caused by the step input current. And afterwards, the neuron is still adapting. The initial intervals are shorter than the final one. So this kind of behavior has been described as initial burst followed by adaptation. And there are many other firing patterns. Now, one-dimensional nonlinear integrated fire models cannot account for this kind of adaptation or burst adapting neurons. What can we do about this? Well, the answer is let's add adaptation variables. Remember, the exponential integrated fire model has a linear term, it has an exponential term, and then it has a current. This is a driving current normally. Now here, the driving current is really given by other variables, W. These are auxiliary variables called adaptation variables. And of course, there is still the external input current. Units of this equation are such that we have voltage here on the right-hand side. So R times I is voltage, R times W is voltage, so W has the same units as I. It has units of a current. Now for each of these adaptation variables, we can write down a linear differential equation. So dW dt has a decay term, minus W. It would normally go back to W equals 0. However, if the voltage is above its resting value, then this drives W to a somewhat higher value, to a non-zero value. The coupling between the voltage and the W variables is A. And then there is an extra coupling, a coupling caused by spikes. These are the firing times of the neuron. F runs from 1 to 3 to 4 to 5, so this is a spike counter. Now, and this is the Dirac delta function. Now essentially this means that after each spike, the value of the W variable is increased by this amount, B sub k. You can have several of these adaptation variables, k running from 1 to 5, for example. And that's why we have this index k here. Tau k is the time constant of this W variable number k. AK is the coupling parameter for this W variable. Often we only work with one single adaptation variable. Now, in the general case, we have already said that after each spike, the W variable jumps by an amount bk. As in the simple exponential integrated fire model, at each spike, and the spike is detected if the voltage reaches the reset threshold, after each spike, we reset to a new initial value, UR. Note that this is reset to, while this is jumps by. It makes a difference, as we will see in the following. So this is general situation. We could have, for example, 5 of these adaptation variables. The simplest case is that we only have one adaptation variable. In this case, we don't need the index k. And in this case, it's called the adaptive exponential integrate and fire model, or short AdEx. Now, what is our aim? We introduced this adaptation variable, one adaptation variable, or possibly many adaptation variables, to account for adaptation, to account for different firing patterns. And I've shown already 2 of these firing patterns. And here are more of these. As before, it's a neuron, and the experimentalist injects a step current, a real neuron, in vitro, in a cortical slice. Now, this is the case for weak step current, that the neuron fires regularly. It fires tonically. If you go to a larger step input, it still fires tonically. Then we have the case, that's one neuron. Now we go to a different neuron. Then we might find a different result. We may find that initially the neuron emits a burst, and then there's a rapid transition to regular periodic firing for low input and also for high input. And then there's, in yet another neuron, we may find that if you give the input, there's indeed this regular firing. However, it takes a long time, a waiting time or delay, until this tonic firing sets in. Now, other neurons may show other behavior. I've talked about adaptation before. Short intervals at the beginning, long intervals later on. Possibly combined with an initial burst or with an initial delay. Again, this line is for the weak input. The upper part is for large steps. Other neurons may show yet a different behavior. Even though the current is held constant after the switch, the neuron exhibits bursting. There's a short sequence, trrrt, followed by a pause, and then another trrrt of many spikes, trrrt, pause, trrrt, pause, trrrt, pause, and so forth. Now, you may find yet other behavior, for example, a short initial burst followed by a long delayed transient. In short, there are many different firing behaviors. Now, on the previous slide, I proposed one neuron model, the exponential integrated fire model with adaptation, AdEx. Can we account for all these different firing behaviors with just one neuron model? And surprisingly, the answer is yes. Yes, we can. Here again, the tonic behavior, initial burst, delayed spikes. Here the case of adaptation, interspike intervals start small and get longer thereafter. There's delayed spike followed by adapting behavior. And there's also bursting, regular bursting, just initial bursting, bursts that start after delay. So there is a variety of different firing patterns in this neuron model, in one single neuron model. So the question arises, can we understand these different firing patterns? how can all these different firing patterns arise from a model that looks fairly simple? Well, yes, we can understand it by using phase plane analysis. So, I tried to convince you that real neurons show a variety of different firing patterns. And there are simple models with just two equations that can account for this variety of firing patterns. Now, one question is whether we can sit in front of the computer and try to optimize parameters by hand, or whether we can predict the type of behavior we are expected to get just looking at our choice of parameters. Phase plane analysis will help for this. And that will be part B of lecture 2 of this week.